In this experiment, you're going to determine the empirical formula of copper 2-sulfate pentahydrate. Furthermore, you're going to look at the accuracy and precision of a classic general chemistry experiment. Before looking at the empirical formula of copper 2-sulfate pentahydrate, let's talk about empirical formulas in general. We're going to look at the empirical formulas for covalent and ionic compounds here. In the example of a covalent compound benzene, which I know is covalent because it contains no metals, it has 6 carbons bonded to each other and also bonded to 6 hydrogen atoms. This discrete unit in benzene has a molecular formula C6H6. The empirical formula for any compound is the simplest ratio of moles. You'll notice that for every 6 carbons there are 6 hydrogens. The simplest ratio is 1 carbon to 1 hydrogen, so the empirical formula is CH. In another covalent compound, glucose, which again contains no metals, therefore I know it's covalent, the molecular formula is C6H12O6. In this case, there's another common denominator of 6, and the empirical formula is CH2O. For some covalent compounds, like for example water, the empirical formula and the molecular formula are the same, because it happens to be the discrete unit is the simplest ratio of moles. In the case of water, there's 1 oxygen for every 2 hydrogens, so the molecular formula is H2O, and the empirical formula is also H2O. Ionic compounds are a little bit different. Here's an example of sodium chloride. Here, the purple balls represent sodium, and the green balls represent chloride. You'll notice that it exists in a large crystalline lattice, where every sodium is surrounded by chlorides, and every chloride is surrounded by sodiums. In the case of ionic compounds, the empirical formula is generally what is used. So this isn't Na100, Cl100, it's simply NaCl, the simplest ratio between Na, sodium, and Cl, chloride. At this point, you may be asking yourself, why would anyone want to use empirical formula if you can simply use the molecular formula? Well, it turns out that sometimes in the lab, the best you can do is find the empirical formula. Let's look at an example. In this case, an experimenter would want to determine the empirical formula of a compound known to contain only carbon and hydrogen when they experimentally determine the mass of carbon and the mass of hydrogen that were in the compound. Recall that empirical formulas are the simplest ratio of moles. Therefore, we need to convert the grams to moles. In order to do that, we use dimensional analysis, as you have done in the past. We take the grams of carbon and we multiply by 1 mole over 12.01 grams. Remember that the 12.01 grams is the molar mass, which can be found on the periodic table. Grams are on the bottom because we want grams to cancel out. Once we do that, we find the moles of carbon. We repeat a similar procedure, of course using the molar mass of hydrogen, for hydrogen to find the moles of hydrogen. Next, we want to find the empirical formula. Right now, all we have is the moles of each compound. Empirical formula is a ratio of the moles. We need to take a ratio of these two numbers. In order to find a whole number ratio, we need to divide by the smaller number. In this case, the moles of carbon is much smaller than the moles of hydrogen. So we divide both moles by 0.09101 moles in order to determine a ratio. When we do that, of course, the moles of carbon, the ratio is 1 because we divided the same number by itself. In the case of moles of hydrogen, we divide the 0.183 by the 0.09101, and we get a ratio of 2.01. Of course, you know we can't have a 0.01 of a hydrogen. You can have 1 or you can have 2, but you can't have a 0.01. And the reason for this is they're physical things. You can only have integer numbers of them. So we round to the nearest integer, in this case 2. We now have a ratio of moles, but we need to write this as an empirical formula. As an empirical formula, this is CH2. So in this example, the best we could do was determine the empirical formula of the compound. We simply don't have enough experimental information to determine the molecular formula. In this experiment, you're actually going to determine the empirical formula of copper 2-sulfate pentahydrate. You're going to begin by dehydrating the salt, which means removing the water. This is done by heating the salt up. If we know the mass of the salt before we heat it and the mass of the salt after, we can determine the mass of water lost. We can then convert that mass of water to moles of water using the molar mass of water. Next, we're going to determine the mass of copper in the copper 2 sulfate pentahydrate. To do that, we will react the copper sulfate with magnesium metal. In a single replacement reaction, copper metal will form. We will then isolate the copper metal and determine its mass. Once we know its mass, we can find the number of moles. When we know the mass of copper, we can find the mass of sulfate by difference. This poses a problem with this experiment, because if the mass of copper is off, so too will the mass of sulfate, which can cause a cascading error, which may lead to formulas that are far different than CuSO4.5H2O. In this way, you're going to test the accuracy of this experiment. In order to test the precision of the experiment, you're going to do everything 3 times. Said another way, you're going to do 3 trials. You need to do these 3 trials at the same time in order to have enough time to complete the experiment. At the end of the experiment, you will comment on both the accuracy and the precision of your work. In the first part of this experiment, you're going to dehydrate copper 2 sulfate pentahydrate. Before you can do that, you're going to need to get the mass of 3 clean and dry test tubes. You're also going to need to label the test tubes so that you know which is which. It's absolutely essential that these test tubes are clean and dry before you record their mass. You will use the mass of the empty test tube repeatedly when you do your calculations. So if this mass is not accurate, it can cause major problems in your final results. Once you have the mass of 3 clean and dry labeled test tubes, you're going to want to add approximately 0.3 grams of hydrated copper 2 sulfate to each tube. It's very important that you do this experiment in triplicate and that you do the same thing to each of the 3 test tubes at the same time. If you were to do them one at a time, it would take far too long. One nice thing about this dehydration experiment is that the hydrated copper 2 sulfate is a blue color, and when we heat it and form the anhydrous copper 2 sulfate and remove the water molecules, which leave as steam, we form a white compound. So there is a clear color change. You will know the dehydration is complete when you no longer see the blue color. Before dehydrating the copper sulfate, it's important to fill the test tube with the appropriate amount. Because test tubes are an irregular shape, it can be difficult to measure their mass on a balance. In order to measure the mass of a test tube, simply place a beaker onto the balance and tare it. Then insert the empty test tube. Once you have the test tube inside of the balance, you can record its mass. Take the test tube out, add approximately 0.3 grams of copper 2 sulfate, and then simply record the mass again. Make sure you know which test tube is which. Next, we need to light the Bunsen burner. Before lighting the Bunsen burner, it's a good idea to turn it off. The Bunsen burner has 2 components. One for the air, which you want to dial all the way down, and one for the gas, which you want to dial all the way in. Once your Bunsen burner is turned off, you want to simply open the gas about 1.5 turns. Now that your Bunsen burner is ready to go, you're ready to turn on your gas. But before you do that, you want to make sure that your sparker works. In order to make sure the sparker works, you simply want to place your thumb on the arm that moves back and forth, and then swipe it across like this. Once you can get sparks, you're ready to turn on the gas. Now that you have the Bunsen burner ready to go, and the sparker is working, it's time to turn on the gas. To do this, at the bench, simply turn the gas on all the way. Once the gas is on all the way, light it like this. Once you have the Bunsen burner lit, you can see here that I have a flame that's too big. Simply dial in the gas nozzle at the bottom of the Bunsen burner until you have a flame that's approximately 6 to 8 inches tall. It's very important that when you're using a Bunsen burner, you never heat anything with an orange flame. This is because this is incomplete combustion and it will leave soot all over everything. Therefore, we need to add some air to this flame in order to make sure complete combustion is occurring. To do this, you simply turn this nozzle until the appropriate amount of air has been added to the flame. You'll notice that this flame here has a sharp inner cone. The top of this inner cone is the hottest part of the Bunsen burner. Now that we have the flame ready to go, we want to use some test tube tongs. Simply grab the test tube that we're going to heat and gently warm the sides of the test tube. It's very important that you heat up the test tube before you heat the copper sulfate because we're trying to dehydrate the water. If the test tube is cold, we will simply condense the water further up in the test tube. So we want to make sure the entire test tube is good and hot before we start to begin to heat our copper sulfate. Once we've heated the test tube, we then can put the copper sulfate directly into the hot flame. It's now been about a minute of heating the copper sulfate. As you may be able to see, some of the copper sulfate has turned from blue to white. You can also see a small amount of steam leaving the top of the test tube. Every once in a while, it's a good idea to just bring the test tube back down to make sure that you're keeping the test tube nice and hot. It's now been about 2 minutes, and as you can see, the copper sulfate has completely changed color from its original blue color. Copper sulfate is now completely dehydrated. Now we just need to simply cool the test tube down and record the mass of what's remaining. One of the single most dangerous things you're going to use in the lab is the natural gas. This is because if it's left on, it could literally cause an explosion. So it's very important that when you're done using your Bunsen burner, that you turn the gas off at the bench completely. In fact, before you leave the lab, you should triple check that you have turned your gas off to make sure that everyone in the lab is safe. After dehydrating the copper 2 sulfate pentahydrate, you will perform a single replacement reaction and form copper metal so that you can determine the amount of copper in the copper 2 sulfate sample. First, the copper 2 sulfate will be dissolved in water, making an aqueous solution. Then, solid magnesium will be added. The copper 2 sulfate solution will appear as a blue color. The magnesium metal is chunks of shiny metal that you'll cut into small pieces. During the reaction, the magnesium will replace the copper. Magnesium will go from a charge of 0 to a charge of 2+ in magnesium sulfate. Therefore, the magnesium will be oxidized. At the same time, the copper will go from a charge of copper 2+ in copper 2 sulfate to copper metal, which has no charge. Therefore, copper will be reduced. Ultimately, what you will visually see is copper metal will form in the test tube. Once you've dehydrated the copper 2 sulfate, it's now time to precipitate out the copper metal in a single replacement reaction. Before you can do that, we need to dissolve the copper 2 sulfate in water. It's very important that you have a cool test tube before you add water. If you add cold water to a hot test tube, it will crack the glass. So please ensure that the test tube is cold, and then simply add an inch or two of water to the bottom of the tube. You'll notice that the solution instantly turns blue as the copper 2 sulfate is rehydrated. You then want to use a stirring rod to gently swirl the solution until all of the copper 2 sulfate dissolves.
So here we have our rehydrated copper sulfate, which to aid the dissolution, I'm gently stirring with a glass stirring rod. Now that's all clear, I have weighed out 0.06 grams of magnesium. It's kind of tough to see because it's not a lot. You don't need a lot to do this. So then we bring them together to start our reduction. Okay. Alright, and if you look closely, you can start to see things floating around. You can see a little bit of fizzing. Now that's going pretty good, but we want it to go faster. So that's going in our hot water bath, which is a beaker with 150 mils of water set to 350 degrees. So, because this is a volatile reaction, I want this to point away from me and my classmates. And I have one test tube here. You are going to be doing this, obviously, 3 times. You did take the time to flame the 3 test tubes. So we're going to pause the video here. You want to let this cook for about 6 to 8 minutes. And when it's done, we'll come back and you'll see a completely different solution. So here we are a few minutes later. And you can see that our reaction looks very different than it did before. This brown color is actually fine copper powder. So our single displacement reaction has completed. And now we still have, you can probably see, some chunks of unreacted magnesium floating around. We want to get rid of that because we intend to isolate this copper by itself. So to do that, we are going to carefully add a couple drops of 5 molar HCl. I'm wearing goggles, gloves, and a lab coat. So are you if you're handling this. I know the lab's probably 1,000,000 degrees. This stuff is hotter. Be very, very careful. Just a few drops. And you see how that immediately begins foaming and turning clear as we react to magnesium. Let this sit for a couple more minutes before you add the rest of that pipette. Alright, it is now 2 minutes later. I know this might be a little disorienting for you watching on YouTube. So now we're going to get rid of the rest of our magnesium. The foaming has decreased in intensity, and I'm adding this very slowly. You can see the foam is rising and frothing, and so we want to be very careful. You do not want this to overflow onto the hot plate. That would be not optimal. As it is, we're going to get rid of this magnesium. This will cook for another 2 minutes to make sure we get rid of all the extra metal, and we will just have some nice copper and soluble compounds in solution. So to recap, we added our magnesium. We let it cook for about 7 to 8 minutes. If you see any blue color, you got to let it go a little longer. Then we added 2 drops of HCl and let it cook for another 2 minutes. After that, we added the rest of the pipette, and we're letting it go for another minute to 2 just to make sure all this foaming dies down. So here you can see our finished reaction. But while we have our copper, we are not ready to get rid of all this liquid yet. If we do, we will probably end up pouring off most of our copper. It's just a loosely packed powder in the bottom. To compact it, we're going to put it in this centrifuge, which will spin the test tubes very rapidly and compress that copper into a nice pellet. So we want to put our test tube, just because I'm a creature of habit, I put it in position 1. Now, if you attempt to run it like this, this will make a horrible noise and shake itself right off the bench. And that would be very bad. These are about $500 each. You will also lose all of your results. So instead you have to balance it. So here, because I'm only doing 1 trial, you'll have 3. I have a test tube of just water. And I put it in the 3 position, and then in the 5 positions. So I have all the odds filled. There's also a 4, 6, and 2, so you can run 2 groups in this at the same time. As long as these points are equal, you're okay. To make them equal, you need to make sure that the amount of stuff in the test tube is broadly equal. Now remember that copper is a lot more dense than water. You have to allow for that. So we'll put these back. So this should be properly balanced. We make sure our speed is set correctly. This is the speed dial. And you want to spin this for about 2 minutes. So that's just 2 ticks. So you've done a lot of chemistry so far. You have dehydrated your copper sulfate. You have performed a single replacement reaction where you extracted the copper from solution using magnesium metal. And now you are going to spin this down, and you are going to isolate your copper powder. The way you will do this, once this is done, is you will very carefully pour off the liquid on top into a beaker. Please take great care not to pour out your copper. If you do that, you have just lost that whole trial. You can't put it back. So you want to pour very slowly. We'll demonstrate that when this is done. So our centrifuge has finished its run. We will let it come to a complete stop. These are not the fancy ones that have brakes, but you see now it is stopped. You can open up the lid. We are at position 1. And you can see that the copper is a lot more squished down into a pellet. You can actually see it move a little bit. So, now we have our beaker, and I'm doing this in the air so you can see it. Please don't do it like this. Do it on the bench, and especially don't do it over the equipment. This is an acidic solution, and you just very carefully, very gently pour off that liquid. Water, of course, has a lot of surface tension, so it might require gentle coaxing. Okay, so now you see we've gotten most of the liquid gone. Now that we've taken great pains to get rid of the liquid, we're going to add more water to it and spin it again. Because, like I said, this stuff is acidic, and there's a tiny bit left, so we want to wash our copper again before we dry it. So, to do that, we're going to get our wash bottle, and you want to suspend as much as you can to make sure you get any little pockets of HCl compressed in your pellet. There you go. Notice how the nice heavy copper dust just falls right to the bottom. Alright, since we are adding liquid, we once again want to make sure that we are properly balanced. We are. And spin it for another 2 minutes. Alright, so we did our 2-minute run. We are going to wait for it to come to a complete and safe stop. And in the meantime, you can start pulling up your Excel, because once we drain this and pop it in the oven, that's where we're going to go next. So I will see you in Excel.
And here we are with Excel. So we have entered our masses during the experiment. First we have the masses of our empty test tubes, which we took at the beginning. Then we have the mass of the test tube with the approximately 0.3 grams of copper sulfate pentahydrate in it. Again, we took that at the beginning. Then we dehydrated our copper sulfate, and once the test tubes were cool enough to handle, we massed them again and got these masses. Notice how the mass is a little lower than here. And then we did the single replacement reaction with the magnesium. We centrifuged our copper powder, decanted off the water, spun it up again after our rinse. Then we dried it in the oven, and we got these numbers once everything was nice and cooled off. So, what are we doing here? We are trying to find the empirical formula of copper sulfate pentahydrate. However, it is very hard to measure moles, and an empirical formula is the least common terms ratio of moles of components in a compound. It's hard to measure moles, but it's very easy to measure mass, and we can convert from mass to moles using the molar mass. So the first thing we have to do is get the weight of all the glass out. We don't want the mass of the test tube in there anymore, and so to get rid of it, we take our mass of the copper sulfate pentahydrate minus the mass of the test tube, and that's how much just plain copper sulfate we have. You can see that we put a little bit of a light amount in. That's okay. It won't hurt the experiment. Then we have our dehydrated copper sulfate. Again, take out the test tube. We now can clearly see that this is considerably smaller. That's a good sign. You dehydrated it. You drove off the water, which then brings us, of course, to the water. Now, at some universities, what they do is they catch the water and recondense it, and then they mass it. This is prone to errors. You don't catch all the water. You don't pour it all out to remeasure. Instead, we let it go into the air, and we find the difference between the dehydrated and the hydrated copper sulfate. Since we don't want a negative number, we always subtract the larger number by the smaller, and we get our mass of water is about 91 milligrams. So then the next thing that we do is we find the moles. To find moles, earlier in the video, Colin went over how to calculate an empirical formula from masses. So just like he did, we take our mass and divide it by the molar mass. Now, here, the molar mass is 249.69. I strongly recommend that you use the molar masses in this video rather than what you might find online, because the molar masses in this video were used to calculate the answers to your quiz questions. If you use different numbers, you might get slightly different answers, which may not necessarily appear in your options. So then we take the moles of copper sulfate, which is the mass of it, divided by the molar mass, which in this case is 159.60. And then the moles of water, which is the mass of our water, divided by the molar mass of water, 18.02. Now notice something. You see how this is 0.001 and this is 0.005? This is about 5 times as much as that. We are working with copper sulfate pentahydrate. Penta coming from the Greek for 5. So we should have about 5 times as many moles. And it turns out we have 4.9. That's pretty good, because remember that in the empirical formula, it's always an integer. It's least common terms. So 4.9 will round handily to 5. Okay, so now that we have this trial done, we have these other trials. You could go ahead and repeat all the calculations, or because Excel is a giant calculator and it wants to be your friend when working with lots of numbers, you highlight these cells, you click on the little green box, and you drag it to the right. You now have all of your numbers. We see that our average, well, not our average, we see that our mole ratios are approximately 5, and they look like they'll average to something close to 5. Now we can move on to sulfate and copper. So once again, the mass of our copper, get rid of the glass. Now mass of sulfate. Sulfate is something that we did not collect. You can't collect sulfate. It doesn't come in a bottle. I wish it did. It would make so many things so much easier in chemistry, but it's an ion. Instead, we exchanged it with the magnesium. So we had solid magnesium, and we had aqueous copper sulfate. We added the magnesium, and then we had aqueous magnesium sulfate and solid copper. We poured off all the magnesium sulfate solution, and we were left with our solid copper. So all that sulfate that was here got poured off, and we were left with just the copper from here. So once again, we find this by difference. So now we do the moles, because there are multiple parts to our empirical formula. It's CuSO4 dot some amount of H2O. But how many Cus? How many SO4s? That's what we've got to figure out. To do that, we need the moles. So the molar mass, or more appropriately, the atomic mass of copper is 63.55. The molar mass of sulfate, even though you can't actually isolate it, you can come up with a molar mass for it, is 96.06. And then the ratio is just going to be that divided by that. One note when ratios, and I skimmed over it here, you always take the first number divided by the second. So it is sulfate to copper here, it is water to copper sulfate here. If you flip this around, you see this is about 1.03, then that'll be less than 1. And that would be a ratio of copper to sulfate. So now we drag. All right. And similarly, if you flipped these over, they would be slightly more than 1. And would still be copper versus sulfate instead of sulfate versus copper. So you have now calculated the moles in each trial. So let's come up with our average values so we can start coming up with a proper empirical formula. Okay, so our average amount of water is 4.86. That, again, must be an integer, and that will round very handily up to 5. How consistent is this number? That's what the standard deviation tells us. It tells us the precision. but it tells us in absolute terms. It tells us that we have 4.86 plus or minus 0.2. Is that good? It's hard to say. So we look at the relative standard deviation, which is the standard deviation divided by the average times 1,000. And we get about 40 parts per thousand, which is pretty decent. Thinking of RSD is kind of like imagining you measure the height of a person in inches. You can get fairly accurate. But some people are like at half an inch, and you're only allowed to use whole inches. So that gives you one measure of precision. That's their height, plus or minus an inch. You then measure the distance from Albany to Troy in inches. And that is some number of miles, I think about 12 miles, plus or minus an inch. The RSD is going to be much, much lower on the Albany to Troy measurement than on the person height measurement, simply because your standard deviation is so much smaller compared to your overall measurement. So that measurement is far more precise, even though they have the same absolute precision given by the standard deviation. Now we have our percent error. How good is our ratio? Another way to think of it is how many points off are you if you were being graded on your accuracy and precision. In this lab, you are not being graded on your accuracy and precision. In fact, the whole point is to examine the accuracy and precision. So do not worry about being graded as long as you put in an honest effort. So to calculate the percent error, the first thing we do is we set up absolute value bars. That's what this ABS does. As you recall from high school, absolute value gives you the distance from zero. It's always a positive number, even if you're subtracting something that would normally come out negative. The absolute value of 1 minus 2 is the same as the absolute value of 2 minus 1. In this case, we take our experimental value, which is our average, and we subtract from that the expected value. This is the ratio of water to copper sulfate and copper sulfate pentahydrate. Remember, penta means 5, so our expected value is 5, and then we divide by the expected value, multiply by 100, make it a percent. And so we're 2.8% off. For what this experiment is, that's very good. That's a 97.2 on your test. So, not much to complain about there. Now we do the sulfate to copper. Take the average, take the standard deviation. So we see that our average is close to 1. That's good. We want it to be close to 1. Then we find our RSD. Okay, 60, not too bad. Again, for what we're doing, for some experiments, 60 is not good. For this, that's pretty decent. And then again, percent error. So we take our average. Now in this case, what should our expected value be? We're looking at the ratio of sulfate to copper. If all goes well, you were provided the right compound, you were able to break it down correctly, it should be a 1-to-1 ratio, right? So you subtract 1 and you divide by 1. Mathematically, you don't actually have to divide by 1, but for some people it helps with keeping the books neat. And you get a percent error of about 2.7. So you're about as good as here. So fairly accurate, which makes sense. That's very close to 1. Relatively precise. And that is the data analysis for your empirical formula lab. I hope this video was helpful to you, and I look forward to seeing you in lab.